10-4.
Live with the North Carolina Museum of Natural Sciences in beautiful downtown Raleigh, it's Science Tonight. Now here's your host, Chris Smith.
Good evening, everybody. Hey, welcome to Science Tonight. I am your host, Chris Smith. I work at the North Carolina Museum of Natural Sciences, and you've made it to our weekly Thursday night show where we talk about all things science and talk to cool people making interesting discoveries out there in the world of science, technology, engineering, mathematics, and sometimes beyond. So thanks for joining us. We've got a great show for you set up tonight. Tonight's episode of Science Tonight is part of our annual Astronomy Days celebration. So we started on Monday last, and we're continuing with Astronomy Days through the end of the week, where each day we're bringing you exciting science presentations with astrophysicists, people who make rockets, people from NASA. Check out naturalsciences.org to get the lineup, the schedule of presentations, and sign up for the ones you think you'd like to participate in. It's kind of like a week-long astronomy convention, all virtual and all free. So check out naturalsciences.org and get signed up to learn some new and cool stuff. You can even do yoga with us. I think there's some astronomy yoga sessions remaining in this week. So don't miss it. You're going to want to check it out. For tonight's edition of Science Tonight, I have a very special guest, someone who's been at the museum, given a couple of presentations in the past, and is always a thrill to have on the stage. I'm so glad that Dr. Katie Mack could be with me on the virtual stage for the museum tonight. Katie, welcome to the show.
Thank you, Chris. It's good to be here. I wish I were actually there, but you know.
That would be nice, right? But in lieu of that, this is not too bad. We've got a great crowd. I've got the videos pulled up here where I can see everybody hanging out in the chat, and I can see how many people we have tuned into the stream. So there's a great, oh, hi, Cindy. I'll wave back at you. So yeah, we've got a great crowd here to learn some new stuff about, the universe. Right. So everybody, I assume most folks globally are familiar with Dr. Mack's work, but Katie Mack is an astrophysicist, cosmologist, and assistant professor at North Carolina State University. Katie is also the author of a much lauded, acclaimed, and soon to be awarded, I'll just speak that into existence if it hasn't happened yet, of the book, The End of Everything, Astrophysically Speaking, which I will be completely honest, I am now only 2/3 of the way into, because astrophysics is not my strongest suit. So I read a page and then I go back half a page and I read it again just to make sure. But that's just me. Otherwise, this book is phenomenal.
Thank you.
It's really good. Like normally, if this were another book, I would go back 3 pages. I'm only going back. I'm kidding. But no, the book is great. Everybody, I'll drop a link in the chat in a little bit where you can pick up your own copy, signed copies, right?
Yeah, copies with signed book plates anyway. So there are these little stickers with my signature that you can get that are stuck into the book if you order from Quail Ridge Books in Raleigh. So might be something you're into. I wish I could do signed actual signings, but again, we got to make do at the moment.
We're making do. So yeah, I'll put the link there in a minute. Everybody, the way that the show is going to go tonight is I have a little game for Katie to play, and then we'll talk about some of the serious science. So we'll play, then we'll work, and then you have the chance to ask your questions. So use the chat and the comments features right there if you're watching on YouTube or Facebook. Leave your thoughts and questions. We'll be monitoring those, and I'll ask those in the Q&A at the end of the show. But tonight, because it is astronomy days, I have a very extra special treat just for all of you, but you have to stay until the end of the program in order to see what the very special thing is. You won't want to go anywhere. Stay tuned the whole time. It's going to be exciting. I promise. I promise. But first, Dr. Katie Mack,
Yes.
you are an expert in all things astrophysical or nearabouts.
Something like that.
Something like that. Okay. Well, at least when it comes to the end of the universe,
Yes.
you seem to know quite a lot. So I thought that I would pose 3 trivia questions for you, all about great endings in television history.
Okay.
I think of it as like how these TV universes ended everything.
Okay.
2 out of 3 will put you in the Science Tonight Hall of Fame. If you get them all wrong, we put you in the Science Tonight Hall of Shame. All right. So let me bring up your first question.
Okay.
Now, number 1, what was the highest rated TV series finale in television history? Was it MASH, Dallas, or Game of Thrones?
I have no idea. I mean, a lot of people watched Game of Thrones, and based on the amount of angry, commentary about the finale, I think a lot of people saw the finale. So I guess I will guess that one.
Game of Thrones is your final answer?
Yeah.
That is incorrect. Ooh, I'm sorry. MASH was the correct answer. 105.9 million people tuned in to the MASH finale and remains the most watched and the highest rated. Everybody loved it. Compared to Game of Thrones, where I don't think anybody loved it.
No.
All right, let's do, okay, there's 2 questions left. You can still pull this off. What is considered broadly to be the worst series finale ever? Is it Big Bang Theory, Game of Thrones, or Dexter?
I've not seen Dexter. I have not seen the end of the Big Bang Theory. I'm gonna stick with Game of Thrones. We're gonna try that one again. See how it goes.
Gonna try Game of Thrones again?
Yeah.
So you're locking in B. Is this your final answer?
It is, yes.
Let's see what the correct answer is. Ooh, oh no. Oh no, Dr. Mack. I found something that you don't know anything about.
I don't watch enough TV, apparently.
You're too busy writing amazing books and being an astrophysicist.
The problem is that most of the TV I watch is about spaceships, and none of these have spaceships in them. So this is making my life very difficult.
I should have done more spaceship questions. All right, well, let's see if we can keep you out of the Science Night Hall of Shame. Here's your last question. How about one with a spaceship? Can you guess the last line of Star Trek: The Next Generation? 5-card stud, nothing wild, the sky's the limit, bring me that event horizon, or engage?
It's definitely not B. And I have watched the entirety of Star Trek: The Next Generation more than once. I don't entirely remember the last line. I think I'll go with engage, though. That sounds fitting.
You'll go with engage.
Yeah.
Sounds like a fitting ending.
Yeah.
For Jean-Luc Picard.
Yeah.
Well, Astro Katie, the correct answer is not engaged. I'm so sorry. Oh, I'm so
terrible.
Sorry. 5-card stud, nothing wild, the sky's the limit. Yeah. Well, I guess I should ask you about things that you do know a whole lot about. Thanks for playing. Now it's your turn. You ask me 3 trivia questions about the ways the universe will end, and I guarantee you we'll be even.
Next time, I'll be sure to stump you.
I don't think it would be difficult. I don't think. Well, wait till I finish the book and then let's go.
Okay.
And then I'll give it a shot. Yeah, sky is the limit, not engage. And maybe engage was too hard of a question to put in there. Anyway, so Katie, for folks who might not be familiar with you or your research, I can't imagine that being the case, but give the folks watching at home a sense of what it is you do as an astrophysicist.
So I'm a theoretical astrophysicist, which means that I study the universe from a theoretical standpoint, meaning I don't use telescopes and I don't do experiments. I sort of think more about the sort of big questions of how the universe is put together, how it works the way it does, what it's made of, all of that kind of thing. And the sort of area I work in, I study a lot about dark matter, which is this invisible stuff that sort of holds galaxies together and is sort of underlying all the structure in the universe, galaxies and clusters of galaxies, so on. We don't know what it is, but we know that it is out there and providing gravity that kind of holds things in the cosmos. And I also study the early universe, so the period of time right after the beginning, and how the universe was evolving at that time and how things were different and what we can learn about, the way that physics works from the very beginning of the universe. So those are kind of my main things. And then lately I've been getting really interested in the end of the universe and how that might happen, and what we can learn from new observations and what we can learn from studying the early universe to learn about how the universe is going to change in the future and so on. But yeah, my time is spent mostly with the computer and with equations and with reading papers and talking to people. And I don't go to telescopes and I don't do experiments, but I try to figure out how to learn about the universe by talking to the people who do use telescopes and experiments, and talking to people who are coming up with new theories and trying to make new connections between those areas. Like how can we test the cool new theory with the cool new telescope? That kind of thing.
Okay, it seems like an interesting spot to be in the astrophysics community, because the folks running the telescopes aren't going to have the time to do what it is you do, and the folks who are trying to dream up new ways for physics to work don't have the time to try to run up to the telescope and chat with those folks. So there's this cool little swirling ecosystem of people that work together. So
yeah.
Go ahead.
Yeah, it's helpful to have some people working kind of in the middle. It's an area we sometimes call phenomenology, where you kind of know what's going on both sides of that story, and you can kind of translate the science between the two, between the theory side and the observation or experiment side. And yeah, it's kind of helpful, because then you help the people who are doing the actual measurements to know what's the big picture thing that we're going to get out of this, and then the people who are doing the theory thing, you get to help say, okay, let's take a grounded look at this, and how can we actually test these ideas.
You said you spent a lot of your time thinking about the beginning of the universe in this space. What's an example of bringing those two things together for how things got started?
Yeah, so we think that in the very beginning of the universe, there was this very extreme expansion that happened that we call cosmic inflation, where the universe expanded very rapidly in the first, sort of tiny microseconds of the universe, tiny fractions of a second. And so it would be really useful to know if that actually happened. And there are some reasons to believe it did, and there are pieces of evidence, but it's not entirely clear what happened there or how. And so we can use observations of the sky, specifically observations of the microwave emission that comes from all over the sky. So it's a kind of, just a kind of electromagnetic radiation that's in the universe, ambient through the universe. It's called the cosmic microwave background, and that tells us something about the very beginning of the universe. The reason that that tells us something about the very beginning of the universe is because it's actually the afterglow of the Big Bang itself. It's actually cooler than that. It's more interesting than that, because the cosmic microwave background is this glow that's just throughout the whole universe that we see using microwave telescopes, using telescopes that pick up microwave radiation. And what that glow is it's a direct view of the universe at the time when it was still on fire. So at the very beginning, the universe was hotter and denser and in some sense smaller than it is today. So, 13.8 billion years ago, all of space was filled with this hot plasma. Everything was super dense. It was sort of glowing with heat, right? And then over time, the universe expanded and that space cooled and the plasma cooled down and became just sort of mostly hydrogen gas. And for a long time, nothing happened, and then stars started forming, and we got the universe that we see today. But during that, at the time when the universe sort of cooled down from that hot phase to this sort of cool, dark universe, we can actually see the moment when that happened, because when we look out into the universe, when we look out into the distance, we're looking back in time. So every time you look at anything, you're looking back in time. If you look at something that's on the other side of the room, you're looking at a few nanoseconds ago, because it took light a few nanoseconds to reach you from the other side of the room. And so any information you're getting from the bookshelf over there is the light took a few nanoseconds to reach you from that bookshelf, and that's how you see it. And that gets more extreme when you look out into the cosmos. You can see stars that are so far away that light took hundreds or thousands of years to reach you. So you're seeing an old picture of them. You're seeing them as they were in the past, hundreds or thousands of years ago. And when you look at other galaxies, you can be looking at billions of years ago. And you can just kind of keep going with that. And eventually you can get to a point where you're looking so far away that the light has taken almost the entire age of the universe to reach you. And that means that you're looking at a universe that's younger and younger. You're looking at the universe closer and closer to the very, very beginning. And at the beginning, the universe was hot and dense. So you can look so far away that you see parts of the universe that are still on fire, where the light has taken so long to reach you that that part of the universe is still in that primordial fireball stage. And that's the light that we see as the cosmic microwave background. That's this glow that's everywhere in the universe. The light from actually looking at a universe that is still on fire. And the reason we see it in microwave frequencies is because the light's been kind of stretched out by the expansion of the universe. If we were there at that time, it would be brighter and hotter, sort of higher frequency radiation. But yeah, we see it as this microwave light, and we can study the properties of that light to learn about the very, very early universe and what was going on at that time and what's been going on since then. And we can learn about sort of how the universe was set up. Like we see that light is a little patchy. We see that some parts are a little bit sort of hotter than other parts. And we can take that patchiness and feed that into a computer and do simulations with it and show that those sort of denser parts of that light, those are the places where the universe is gonna, that's gonna grow into a cluster of galaxies. And because it's a little places where the universe is a little bit more dense there, and so gravity is going to pull matter together, and that's going to make a galaxy and clusters of galaxies and so on. And we can actually do all that with a computer and show that if we just take that data from the patchiness of this cosmic microwave background, this light coming from everywhere, then we get a universe that looks like what we see today, with galaxies and clusters of galaxies and solar systems and all of that. So it's an amazing tool that we have, that we can see this background light.
It's phenomenal, because I don't know how that concept of the entire universe fits inside somebody's brain. Maybe it's only 7, it's like not even 7:30 yet. And already these concepts just are like, they seem too big for my
Yeah.
brain to like really wrap around and understand. And I've seen some like cool animations and stuff, and done by museums, in fact, where they sort of show the cosmic microwave background, and you see it as this this sort of sphere of blues and reds, hot and cold zones, and then these tendrils, these that sort of form out of that, these networks that connect. I guess where gravity's pulling things together.
Yeah, yeah.
But then you mentioned in the opening there that that sounds like sort of normal gravity. Big things pull, everything just sort of starts to coalesce and come together, and you've got a universe. But you were actually talking about dark matter, which is, as I understand, is something entirely different.
So dark matter is a kind of matter. So matter is just anything that's sort of has mass in the universe, stuff. So dark matter is a kind of matter that that is different from regular matter, from the kind of stuff that we're made of, in that it doesn't seem to interact with light. So it has gravity, it has mass, and it is, sort of the most of the matter in the universe. 85% or so of the matter in the universe is this invisible dark matter, and the stuff we're made of is just kind of an afterthought, just sort of sprinkled on, mixed in. But so that was present at early times. It was present in, at the time we see when we look at the cosmic microwave background, and it was sort of what drove some of that gravitational collapse. But the weird thing about dark matter is that it appears that it just doesn't interact with electromagnetism at all. So what that means is that we can't see it, it's invisible. So light will pass right through it without reflecting or being absorbed, or won't be emitted by this stuff. But that also means that it's untouchable. It means that you can't hold on to it, you can't touch it, because the way that you touch anything is that you sort of push your electrons against the electrons in the other thing. So everything is made of atoms. Atoms are like a nucleus, and with a little electrons zooming around the outside. You've probably seen these kind of pictures. And those electrons repel each other. And so the atoms in my hand are repelling the atoms in my other hand. And that's why my hands feel solid to me when I touch my hands together. And so if you don't have, and that electric repulsion is electromagnetism. It's sort of passed from one thing to another by photons, by particles of light, by these sort of electromagnetic signals. And so if you have stuff that doesn't deal with electromagnetism at all, it doesn't deal with light at all, then it can't do that repulsion thing, which means that it'll pass right through itself and other matter without getting stopped. And that's important for the buildup of structure in the universe, because if you take a whole bunch of gas and dust and you try and compress it into a sort of sphere or something like that, it pushes back. It has pressure, and so it's kind of harder to get a big clump of it together. But dark matter doesn't have that pressure, and so it can kind of just gradually coalesce without getting without sort of bouncing off. And so it sort of acts as this extra glue that helps bring in the stuff that has pressure and give it like extra hold inside, so that it's able to really get together and form galaxies and clusters of galaxies and so on. And so dark matter is like this extra glue that brings together all of the matter in the universe, that helps us to have things like our galaxy. Like our galaxy wouldn't form without this dark matter helping to pull the matter together.
So that sort of naturally moves us into the end. In some way, it's like, oh, okay, these forces have brought everything together. We've got a universe. Now let's end it all.
Right.
And in your book, The End of Everything, you talk about how the universe came to be as we know it. But that's sort of like the precursor to get us into understanding the very interesting ways that the whole thing could be done.
Yeah. Yeah.
Is
So
there, well, I was about to say, do you have a favorite way the universe ends? And maybe we'll start with that one.
I do. I do have a favorite way the universe ends, but that one's kind of the most complicated one to explain. So my favorite way for the universe to end is called vacuum decay, and this is one of these things that just kind of comes out of nowhere. Um, the usual way we talk about the universe ending, the reason we think that the universe will end is because we look at the expansion of the universe and we see that that naturally leads to a sort of untenable position for the universe, something that an evolution toward a state where the universe just can't exist anymore in any hospitable way. So when we look at the history of the universe, we see that the universe started in this very hot dense state, and it's been expanding ever since then. And if that expansion continues, then that just sort of changes what the conditions in the universe are like. And so we see how the universe has been changing over time. We see that at different times there were more stars being formed than now, or there were galaxies were coming together more often than they are now. And we see over time that as the universe evolves, as the universe continues to expand, everything in it is getting kind of more and more isolated. Clusters of galaxies and galaxies that are isolated from each other. They're getting farther and farther apart. And so the universe is getting sort of more dark and empty and cold. And that's the sort of evolution toward some kind of ending that we sort of expect to see. Because if you just just extrapolate this expansion into the future, you get a universe that's so big and empty and dark and cold that there really can't be anything in it anymore, and it leads to what we call a heat death, which is just where the universe sort of fades away. And that's our usual picture of the end of the universe, which is not a fun story. It's kind of this depressing.
Cold and alone. No, I
Yeah,
don't think
yeah,
so.
yeah. It's not a fun picture, but the thing is that there's there are lots of different ways the universe can end, and none of them are nice. It's not going to end well. There are some that are more violent, where the universe could be ripped apart or collapse on itself or something like that. The reason I like vacuum decay as a possibility is that it's really something that just comes out of nowhere, and
Oh,
can
okay.
totally sort of rewrite the laws of physics throughout the universe in a way that destroys everything. And it's something that has only been really talked about seriously in the last sort of decade or so, as something that could really happen in our universe. And we don't know for sure if it could, and if it did, it would probably be so far into the future that the universe would basically be sort of cold and dark and empty already anyway. But the way it happens is that you get this sort of quantum transition somewhere in the universe that creates this bubble of a different kind of space where the laws of physics are different, and where atoms don't hold together anymore. And that bubble expands the universe at about the speed of light and just destroys everything. And the fun thing about it, if you're a physicist, is that it's totally unpredictable, in the sense that you don't know exactly when or where it would happen. Although again, I can say with pretty good confidence it's going to be a very, very, very long time from now if it happens at all. And it's neat because you have this weird connection between the physics of the very, very small. I mean, this is something that's powered by a quantum transition, a quantum tunneling event, which is something that really only happens on subatomic scales. And then something that tiny can trigger something that can expand throughout the entire universe and just destroy everything. And that connection between the very, very small and the very, very big is fun if you're somebody like me who is interested in both particle physics and cosmology and the universe as a whole. So if you want to know more about that, you'll probably have to read through that chapter in the book. But it's sort of the most random in every sense of the word way for the universe to go, and it would be it'd be very quick and painless. You wouldn't see it coming, so that part's nice.
Just the snap of a finger and
Basically.
existence is gone.
Yeah.
And And no indication that on the other side of that bubble, we could just still be there, but we would just be different.
No.
It's just over.
No.
That's a great way to end the universe, though, right? Like, it's quick.
Yeah, no, it's very
painless,
clean, and and it's very final.
It erases everything.
Yeah, all indications are that once you're inside the bubble, you then also collapse into a black hole. So it's really over at that point.
You just collapse into a black hole. Okay, well, so this is interesting. You said that this is kind of new. What does it take to come up with new and exciting ways to end the universe?
Well, so vacuum decay as a concept has been around for longer. I think the first papers about it were in the 70s or 80s, but it was sort of a theoretical idea, and it was built around our understanding of how the universe evolved during its first moments. So there's this idea that very early in the universe, the laws of physics were different. There's something called the Higgs field, which is this energy field that pervades all of space. You probably heard about the Higgs in terms of the Higgs boson, which is a particle that was discovered at the Large Hadron Collider in Geneva. The Higgs boson, the talk around that, people say that it has something to do with how particles got mass in the early universe. Really, the Higgs boson is like the particle version of the field, this energy field that sort of is through all of space, and that energy field is what had something to do with how particles got mass in the early universe. But what happened is that very, very early on, something happened where this all-encompassing energy field changed and set the laws of physics differently. So in the very, very early universe, the laws of physics were different. We had different particles, different forces between particles. We didn't have, protons, electrons, neutrons, all of that. We had a totally different mix of things that were interacting in a different set of ways. And then the Higgs field changed. So, this energy field everywhere changed its value. And when that happened, it set up the conditions for the particles we know and love today. It set up the laws of physics that we currently have, and made it possible for, stars and galaxies and life and so on to exist. And the weird, the reason people talk about vacuum decay is they sort of ask the question, like, could the Higgs field change again? And could it go to a different value, one where we cannot live? And that's what happens in vacuum decay, is that somewhere in space the Higgs field changes again, and that change propagates in this scenario. And so, it's really, the way those kinds of theories come out is you're trying to explain something like, the properties of the particles that we have in the universe now, how they interact with each other. And that leads to this idea of the Higgs mechanism, where they, have this Higgs field and it changed in early times. And then, you have that idea, and then you try and sort of poke around the edges of that idea, and what could happen next? What if we have this energy field, like, could it change again? Like, what's governing what value it takes? And you sort of poke around the edges of that, and you play around with those ideas. And if you're not careful, you find out that, it could accidentally end the universe. So, you have these ideas that get sort of built up through exploring the consequences of ideas you already have for other purposes. And there's another one in my book, another scenario like that, called the Big Rip, which is where the universe would sort of rip itself apart. And that idea came about by thinking about dark energy, which is some kind of stuff that makes the universe expand faster and faster all the time. Thinking about different possibilities for what dark energy could be. And it turns out if you sort of play around the edges of that theory, you end up with something that can tear the universe apart. And so, none of these are sort of the favorite ideas, but they're things that we explore as physicists. We think about what would happen, like, how can we rule this out, or how can we find evidence for this being possible, and so on. They're interesting ideas to think about, to explore, to try to find data for or against. And that's kind of the fun part of being in cosmology, is that you get to play with all these different ideas. You get to expand what we know about the universe, and also explore a lot of these sort of what if scenarios.
Well, so in exploring a lot of these what ifs, maybe some of them, you find the edges of the rules, and then you step outside them and you realize that you didn't have a firm grip of the rules to begin with. And some of these scenarios still work out. But why study the end at all? What do we gain? Is it just that we sort of expand the limits of the rules of physics, or is there more to it?
I think there are a couple of reasons to think about the end of the universe. One of them is just that we want to know, right? Like we are curious, right? Like we want to know the beginning of the story, we want to know the end of the story, we want to know the narrative of this universe that we live in, and so we're curious about it, and we want to know what's going to happen next. That's just part of human nature. That we want to study that. In terms of physics, in terms of like what are we going to learn about this that has practical applications for physics, we don't know. I think that it is something that is useful to think about because it helps you it helps kind of spark your creativity about theories. If you have an idea of how physics might work in a certain situation, and then you extend that to well, what does that say about the far future, and what would that tell us about how things are going to evolve over trillions of years? That can kind of give you new ideas for how to refine those theories, how to better understand just the universe we live in general. And so it can be good as one of these thought experiments that just kind of helps you find the edges of the theory and maybe gives you some new direction to look in. So thinking about for example, vacuum decay has sparked a lot of interest in understanding the Higgs field. And so there are experiments that are being done to try to better understand how the Higgs field works. And so we're going to learn a lot about this mechanism that was so important at the beginning of the universe, and part of that might be because we want to know how it's going to evolve into the future. And it changes how we look at certain kinds of ideas for example, string theory, which is one of these, theory of everything kind of ideas that may or may not work out. But if vacuum decay can happen in those theories, then it has implications for whether or not those theories, make sense. And then it helps you kind of find the edges of what and sort of test, stress test these new ideas.
So then that's what's next for astrophysics or for cosmology or theoretical particle physics, is to figure out if string theory is the theory, or if there's some other way the universe works that we don't know about yet?
Yeah, I mean, there are a few different really interesting big questions in physics and cosmology right now, and they're sort of built around the fact that we have a pretty good description of how particle physics works, because we have these experiments that we can do, and we have what's called the standard model of particle physics that sort of accounts for all of the particles we've ever discovered in experiments, and it seems to work really well. And then we have this great description of astrophysics, of cosmology, where we know that the universe has dark matter and dark energy, and we know how its evolution has gone through time. We think probably there was this cosmic inflation thing at the beginning where the universe expanded very quickly. And these models work really well, but we don't understand the fundamental physics behind any of them. We don't know why the standard model of particle physics works, why we have the particles we have, how they fit into a bigger picture. We don't know what dark matter is. We don't know what dark energy is. We know that the universe seems to have them in it, and it seems to work, but we don't know why. We don't know what dark matter and dark energy are made of, and we know that they're not included in the standard model of particle physics, even though we think that they're probably connected to particle processes somehow. And then we have this theory of gravity, general relativity, Einstein's theory of gravity, and that works really well with all the tests we've ever done. All the experiments seem to confirm it, but it doesn't work with our theories of quantum mechanics, of how particle physics works at subatomic scales. And so we have all these weird inconsistencies where, our experiments are all working perfectly well. Our observations are meeting our expectations, but we don't know where to go to tie it all together. And so something like string theory might end up being the answer. There might be some other idea that comes along that comes out of, trying to push the edges of all these theories. But what we're really looking for is that something that'll tie all that together and put it into the big picture, and that we don't have yet.
Do you think there will be something? Because I'm thinking something that works at the scale of the quantum, of the just the smallest stuff in the universe, and then stuff that also applies to the biggest things in the universe, or the universe as a whole, as one entity. It seems like they could very easily be playing by two different sets of rules, but I'm not a cosmologist.
Well, so there are certain environments where they have to come together or contradict. So, for example, the extreme environment of the interior of a black hole, for instance, you have these extreme forces, very dense region, very small space. Something there is, we can't describe what's going on there with just the understanding of gravity and particle physics and quantum mechanics that we have now. Something doesn't quite fit. There are contradictions you run into. When you look at the early universe, you have this very dense, hot phase where, because it's so dense and so hot, and because everything's packed together, you would expect that particle physics would rule the day there. But it's also, gravity should be present and doing something because it's got so much, energy there, and we don't know how that all fits together. So there are some places where everything really has to fit together. It's there has to be some unifying picture, because our huge universe now seems to have come out of processes that occur on very, very small scales. This inflation process, if it happened, was basically a particle physics event. And it seems to have created the structure that we see in the universe today. So there are these important ties between the scales of the cosmos, the huge scales, and the physics of the very, very small. And there are places where they will come into contradiction based on our current understanding. And so there has to be something beyond our current understanding that should tie it all together, where there has to be something that fixes that disagreement. We just don't know what it is yet.
Excellent stuff. Excellent stuff. Mind bending. But I guess that's what the math is for, right? The math brings it all together.
Yeah. And, all of theoretical physics is really about trying to put together a mathematical description to describe all of the stuff that we see in our experiments, all the stuff we see in our data. And we hope that those mathematical descriptions are getting us closer to what reality is. But we know we're always gonna, maybe we're gonna get closer to that. We might never really know the ultimate truth. That's a harder thing.
Well, everybody watching, if you don't want to learn all the equations, a great way to learn about all of the different ways the universe could end would be Katie Mack's book, The End of Everything.
Yeah, I don't think I have any. I think I might have an equation in there where I say W equals -1. I think there's something like that, but there's really very little in terms of the math. I really tried in the book to bring out the concepts without making it something that you need to know any physics or astronomy to get. So hopefully people find it very accessible, sort of conversational. There's lots of funny footnotes, stuff like that.
Yeah, I'm particularly enjoying the funny footnotes. But you also have a great way of writing, just with like a sort of subtle humor that carries throughout the passages. That just it makes rolling through stuff that would be heavy or heady or could be full of really intense scientific explanation. Just that much more easier to comprehend. So I think anybody we should be able to get through this one and come out the
Excellent.
other side better. So how about some questions from the audience?
Sure. Sounds good.
I see there's lots of questions coming in on the chat. Folks, drop your thoughts and questions for Katie there. And I'm going to grab the first one that came up earlier in the show. John wants to know, does the speed of light seem too slow? It just takes so long to get anywhere.
Does it seem too slow? I don't really know how to answer that. It's I mean it seems to be fixed. So that's a weird thing, you know. It seems like the speed of light is the same no matter how you measure it, no matter what you're doing when you measure it. And that's a weird thing. That's part of Einstein's relativity, where you could be in a rocket traveling at half the speed of light. You'd still measure the light beam going across your rocket as going, if you shine a flashlight inside your rocket, you still see that light traveling at, from your perspective, the speed of light, this particular number. And everybody outside your rocket would also see that flashlight beam traveling at the speed of light. And so they would totally disagree on when it gets to the end of the rocket. I mean, there's weird stuff like that happens because the speed of light is a constant within a vacuum, I guess you have to specify. But it's a strange aspect of our universe. It's what leads to all sorts of weird things with relativity. But I don't know. I mean, I guess our universe could look a little different if it were a little bit faster, but this is the number we're stuck with.
Yeah, this is what it is. Okay, let's see. JP wants to know how these universe endings fit with the concept of the multiverse.
Yeah, so it depends on what kind of multiverse you're talking about, because people mean a lot of different things when they talk about a multiverse. There
are multiverses.
Yeah. So
Okay.
Sometimes when people talk about a multiverse, they mean like parallel universes, like in quantum mechanics. So there's this idea in quantum mechanics that some interpretations of quantum mechanics that say that every time a quantum event happens, a new universe branches off that's just like our universe, but with some, this coin flip went the other way, basically. And so that's something that, like, you could have sort of slightly different histories, slightly different futures in universes like that. But in physics, in cosmology, when we talk about multiverses, we usually just mean parts of some larger space where there's regions that are so far away from us that they might as well be another universe. They're so far away that we can never communicate with them, we can never interact with them, because they're being sort of pulled away from us at more than the speed of light, because the speed of light is not a limit for how quickly things can move apart if all that's happening is the space in between is getting bigger, which is what happens with the expansion of the universe. So there are regions of the universe now that we know are moving away from us at faster than the speed of light. It's not that they're moving, it's not that we're moving, it's just that there's more space happening in between. And so there could be things that are so far away from us that they're basically in another universe, that we'll never interact with them, that we can't see them. And they could have very different laws of physics. They could have different, histories. Those parts of this larger space could have, a different future. So that's one way you can get differences from the multiverse. And then there are also weird ideas where you can have sort of these little pocket universes that actually like slam into each other, depending on when they're formed and how and stuff. And there are certain scenarios where that could affect the evolution of the cosmos. And there's one I talk about in my book that's sort of an old idea that's not accepted anymore so much, but where you could have sort of parallel universes that actually collide and create a new Big Bang. But that's a whole other story. But yeah, so there are a few ways it can come in, but mostly when we talk about multiverses in cosmology, we just mean places where you can have different conditions because they're outside of what we consider our universe, in terms of our observable universe, the region of space that we live in.
All right, excellent. Okay, strap in. Margie says, in the book, you talk about a cyclic universe and how slow contraction pre-bounce can solve the same problems as inflation. Can you explain how slow contraction does the same thing for horizon or flatness as fast expansion, and how we could ever hope to tell them apart in observations?
Okay, so this is a question about the ekpyrotic scenario, which is a cyclic universe idea that was pioneered by a few different people, including my PhD advisor, Paul Steinhardt, and some of his colleagues. And can I explain how slow contraction can solve the same problems? Not in a video call like this, no. Like,
You need that chalkboard back there.
The physics of that gets a
5.
little bit complicated, a little bit subtle, but if you look around on the internet, there are a lot of explainers about the ekpyrotic universe, and there's some actually reasonable, accessible stuff that gets into that. So I'm sorry that I can't get into that so much now, but it has to do with how sort of information is propagating through a universe when it's sort of coming together and versus when it's sort of expanding apart. And under certain circumstances, you can set up these fluctuations that you need to seed the structure of the universe that we see today. But it really would get kind of technical if I got into it now. So I'm afraid I'm going to have to pass on that one.
It's time for a Google search.
Yeah.
Oh no. And looking at the clock, my gosh. But there's a lot of great questions here. I'll get to as many of them as I can. Okay. Hank and Denise want to know if the inflation of the universe, would the inflation of the universe have to have happened faster than the speed of light? It couldn't have, could it?
Well, okay, so this is where you get into the subtlety about the speed of light when you're talking about expansion. So if you have a universe where the universe is just expanding sort of in a uniform way everywhere. So let's say, like, imagine you have sort of a chessboard and you just make it twice as big, and it's just at, the same proportions and everything. Then on that chessboard, the two squares right next to each other, when the centers of those two squares next to each other, when you've made the thing twice as big, they're twice as far apart. So they've gone a little ways over this, like 3 seconds or whatever, where you did this expansion. The ones on opposite ends of the board have gotten twice as far apart, but that means they've traveled much farther over that time period, of that same time period. So in a sense, those two squares on opposite ends are moving apart much, much faster than the ones that were close together in the beginning. And so if you just imagine that chessboard is incredibly large, there's going to be some distance, some squares that were separated by so much that if you did that expansion the same way everywhere, then they're going to be moving apart so fast that they're moving apart faster than the speed of light. Like, there's always going to be some distance, where a uniform expansion will mean that 2 points are moving at faster than the speed of light away from each other, just because the space there's so much space in between, and the space in between is getting bigger. And so if you have more and more space in between, then that means those things are moving apart faster and faster and faster. And so, so that's happening now, that there's parts of the universe that are moving apart away from us at faster than the speed of light, because the universe is expanding everywhere. And in the very early universe, you had that too. And there's sort of a different way that you can count, that you can sort of describe how our view of the universe is changing as the universe expands. And in a sense, when that cosmic inflation happened, if you were sitting there in the universe at the time, your view would have been kind of shrinking, because that expansion would be so fast that things are moving away, that region where things are moving away from you faster than the speed of light is very small, and it's getting smaller. Whereas for most of the period of the expansion of the universe, that region would be getting bigger in some sense. So I'm not explaining it very well, but there's a sense in which you can kind of talk about it as faster than the speed of light at the time, but that's not a clear-cut thing, because it does depend on how far away you were at the time. And so sometimes it's described that way, but I don't think that's a very good description. There are better ways to describe it that probably, again, take a diagram to do well. But it's kind of about whether how much of you can see is kind of shrinking or growing. And at the time, your horizon was really shrinking in that sense, in the sense of like how much of the cosmos you could actually see. And it turns out, because the expansion of the universe is accelerating now, because dark energy is making the universe expand faster and faster, we have a sort of similar thing happening, but on not as extreme a scale, where also things are moving away from us so fast that in a sense, how much of the universe we can see is reducing, but in a sort of subtle sense. But it means that over time we will see fewer and fewer distant galaxies, and eventually we won't see any at all, because the expansion is speeding up so quickly. Sorry, I can't hear you right now. Yeah.
I'm back.
Okay.
Excellent stuff. One last question, because this one came in and it's not related specifically to astrophysics at all, but it's a good question and a good one, especially for you, since you've just now published your first book. Do you have any advice for up and coming science communicators?
I think my advice would be to, whatever kind of science communication you're doing, if it's writing or videos or whatever, you're going to get better with practice. So like, do a lot of that. I've done a lot of science writing, and that's the more you do and the more you get feedback on it, the better you get at that. And then also, sort of listen to how people are talking about the stuff that you're trying to present, listen to how people feel about the topics that you're talking about, really try and connect with people on that level. Find out what's confusing to people, find out what's scary to people, find out what bothers people, because if you really understand your audience, and if you really actively listen to how people conceptualize this stuff, how people feel about the science you're describing, that's going to mean you're more able to connect with your audience. So tailoring your message to your audience is just super important. And in order to do that, you need to be, very actively listening to people, and understanding what their perspectives are.
Everybody, drop clapping hands emojis into the chat box for Dr. Katie Mack for making it through an hour-long program all about cosmology and astrophysics and answering my less than informed questions on the topic. I promised everybody that if you stuck around until the end, I'd have a special surprise for you. And I am going to bring these folks on now. Everybody, I want you to meet the group Living Poetry. I'm going to turn the show over now to an organizer for Living Poetry, Bartholomew Barker. Hey, Bartholomew.
Hey, Chris, thanks. Let me tell you just quick.
What's going on right now.
Sure thing.
Yeah, tell us about your group, and then tell everybody what's about to happen to them.
Will do. So Living Poetry is the largest collection of poets and poetry lovers in the Triangle. We run like monthly workshops. We do a weekly poetry prompt. We've got a book club. We do the occasional open mic, and plus various other just whatever poetry related events we can come up with. So you should check us out at livingpoetry.net or search for Living Poetry on meetup.com, because that's where we organize primarily. So tonight I'm joined by my fellow living poets, Pamela Taylor and Anna Weaver, and we've been enjoying the presentation. And so while Dr. Mack was talking to you, Chris, we've been writing poetry inspired by this talk. I called my poem "Telescopes Are Time Machines," but the title really doesn't affect the rest of the poem, I've noticed. So whatever. You and I, We both know the math. This is all going to end someday. Our sun will nova, our planet disintegrates, the stars will run away from us and slowly blink out. Or maybe some petulant dark god rips the universe apart, or flips a field and we all collapse. But lying here with you in the afterglow of the Big Bang, underneath the star-speckled sky, in the expanding dark, but not made of dark matter, so we can hold each other, stave off decay for a moment. Right now, with you right here in my arms, I can believe the sky's the limit. Thank you.
Brilliant.
And now, Pamela Taylor.
Hello, everyone. I'm greeting you from Brookline, Massachusetts, where I live, but I used to live in Durham and used to be a co-organizer of Living Poetry. And in fact, was the one that got this whole thing started in terms of poets reading with science, about science. So I'm very happy to join you. The pandemic silver lining is that I get to join you today via Zoom. And so my poem is The End of Everything, ? And so I'll read it. The end of everything. The universe is still on fire. Galaxies are still forming. The light that comes from distant corners ignites blues against reds. Every electron pushes back against each other, against itself, beyond what dark matter can hold. We move farther apart, microsecond by microsecond at light speed. How much more can we expand before this bubble bursts? Before we rip ourselves apart, our bodies afterthought sprinkled with stardust? There has to be something that fixes this disagreement. We don't know yet what it is.
All right, I will bat cleanup. My name is Anna Weaver, and I am a poet living in Cary, North Carolina, and my poem is called Trivia Night. In the beginning, it wasn't like it is now. The rules were different and everything was possible. Somewhere in the middle, 105 million people watched the last episode of MASH, and it's been downhill ever since, which is why I've come to accept that we cannot hold what holds us together, that between what we can see and what we can measure is nothing but equations, that all the secrets are hidden in the afterglow, the thin light growing soft, the light growing soft and thin, stretching out as if to say, darling, you know this can't last. It's not you, it's not me, just the space between us spreading apart. But even if you think you can see the end in the beginning, when it finally comes, it's always a surprise. And when it's all over, you'll know, because that day, every question will become trivial. And that wraps it up for the Living Poets. Just real quickly, on behalf of us, I want to thank Katie for the inspiration tonight and Chris for the inspiration we get every time we write for Science Cafe. We really enjoy it.
It is a thrill to have you folks on the program every single time. The poetry is beautiful. And that you come up with such fascinating poetry, such brilliant work in the space of the 60 minutes that we do the program. That's so impressive. Thank you so much, all three of you, for being here with us tonight.
Yeah, thank you. Those were really amazing. I loved all of them. If you could send them to me, I would love to just have them. Thank you so much.
Absolutely, will do.
There you have it, folks. a perfectly fabulous Thursday night full of astronomy and poetry. And I think we all got to know the universe a little bit better in so many ways tonight. So I want to thank Dr. Katie Mack for being with us. Again, the book is The End of Everything, Astrophysically Speaking. You can find it. I dropped the link to the Quail Ridge bookstore in the chat. They've got the signed bookplate version if you wanted to pick it up from there. Next week, next Thursday night, here on Science Tonight, I'll be talking with, we're going to do something completely different. We're going to be talking about millipedes in southern Appalachia. Did you know that there are more than 100 unique species of millipede hanging out in the mountains of the eastern United States? We're going to talk to somebody who's working on describing dozens of new species, some of them right in our own backyards. We're going to be talking with Dr. Derek Hennon from Virginia Tech. You won't want to miss it. We're going to be talking about what will be your new favorite critter by the end of that show. That's next Thursday night right here on Science Tonight. You can check out naturalsciences.org to get more information about Astronomy Days programs that are going on through the rest of the week, or any of the great virtual programs and offerings that we have coming out of the museum every single day of the week, just about. You can also follow the museum on Facebook, Twitter, and Instagram. We're at Natural Sciences. And you can click the subscribe button that's right here below the video, and you click the bell to get notified. And then you don't even have to check the website. You'll know when the next episode of Science Tonight is coming at you live. And then you just click or tap right over, and you learn something new with us out of the North Carolina Museum of Natural Sciences. Katie, I almost forgot. If people wanted to follow what you're working on, how can they do that?
Yeah, you can find me on Twitter at AstroKatie on Twitter, and on Instagram, I'm at AstroKatieMack because the name AstroKatie was taken on Instagram. I'm also on Facebook at facebook.com/AstroKatie. I spend a lot of time on Twitter, and my website is astrokatie.com. So that's where you can find all the things.
Great stuff. All right, from all of us at the museum, I hope that I'll see you all at future Astronomy Days programs. If not, I'll see you next Thursday night for Science Tonight. Good night, everybody. Take care and stay safe.
Good night. Thank you.